This meeting is being recorded.
This next video, I'm going to introduce just a few concepts from 1.12. We're going to just review quickly about dipole moments and this term induction, and then we're going to move on to intermolecular forces in 1.13. So you should recognize this term, electronegativity, and the fact that there's differences in electronegativity, right? We can calculate a difference or a change in electronegativity between our two atoms, and whatever that value is, if it's high enough, we'll have polar bonds. So because of these polar bonds, one end of a molecule might have one pole and the other end might have another pole, right? One might be partially positive, one might be partially negative. We call this result a dipole moment. So this shift of electrons, or induction, is this shifting of electrons within an orbital, can result in a dipole moment. So once we have this dipole that's created, different properties of molecules exist versus nonpolar. So you won't have to do any calculations of dipole moment and conversions to Debye, this unit here, this capital D, but you will sometimes be given values for dipole moments and have to utilize those. So we're going to skip over some of these calculation slides coming up, but know what that capital D stands for, and we're also going to just briefly look at what a dipole moment is. So it's the product of this charge, or E, and the distance between the two atoms that we're referencing. So the dipole moment for the bond is abbreviated as this mu, this Greek letter M here, mu, and the calculation is in these electrostatic units, so ESU for the electric charge, the electron's charge, and then this over here is measured in centimeters. This is our distance. Put them together, you get ESU times cm. The way to convert from this calculation up here is we would divide by a certain amount, and we would end up converting to our units of D, capital D, Debye here. So you won't have to do that. So I won't go into the details of what we divide by, etc., how we determine ionic bond character. Let's see here. So this is how you would calculate all these bond characters, percent ionic character rather, if you needed to. And this here kind of shows you with vectors the molecular dipole moment that results is a net of all of the individual dipole moments between the bonds. So you can see our carbon-hydrogen bonds are nonpolar, but we have a CCl and a CCl bond over here. So their combined vector would be this right here. So this is the molecular dipole moment indicated over here. Again, if we put together all the dipole moments of all the bonds and the lone pair, we get this net dipole moment here, pointing up. And then we see so this is ammonia, and then over here with water, we also have a net dipole moment indicated over here. So just know that the sum of all of these individual bond dipoles creates our net dipole moment in the molecule. So those are the values that are given when you see, 1.87 Debye. So you should know the molecular geometry before analyzing polarity, because if you have vectors that cancel each other out, like within CO2, right, our linear molecule, so we know how to do a Lewis structure, we know this vector goes that way, this vector goes that way, they're equal. So even though each bond is polar, we would see there's no net dipole moment. So that's where the molecular geometry comes in. So assessing the polarity. So this here is electrostatic potential map or just a color coordinated diagram that shows us the more negative regions are in this red. So a lot of electrons there, right? So this is, again, correlates with chlorine. And then these carbon hydrogens, these are very positive regions based on the color scale here. But again, you won't really have to interpret those on any assignments. And then here's just a list kind of summing together some polar solvents that you may see. So we're going to look at the importance of polar versus non-polar solvents in certain discussions. But for example, we have acetone here. This is a polar solvent. It has a pretty high dipole moment indicated here. But that's where we'll end this discussion for 1.12. So let's review some properties that result from these intermolecular forces such as solubility, boiling point, density, etc. So the attraction between individual atoms or individual molecules is what causes them to have these properties. So we have with polar molecules, a dipole-dipole interaction. With very specific polar bonds, we can have hydrogen bonding. And then when there's nonpolar molecules, we still have some kind of interaction called these dispersion forces or London forces, or sometimes they combine that, London dispersion forces. So let's take a look here. These polar molecules that have dipoles, right? So we have a two-pole molecule here, right? This will be a dipole. So this would be a bunch of acetone molecules lined up, and the electronegativity difference between carbon and oxygen is noted to give this dipole within the molecule. And any molecule with a dipole with itself can have dipole-dipole interactions. So they give an example such as isobutylene would have a lower boiling point, which is very nonpolar, versus acetone. So we have dipole-dipole attractions. So here's isobutylene, and they show you the stats down there. And there's the dipole moment indicated with acetone, no dipole moment with isobutylene. So the melting points, the MPs, as indicated up here, and the BPs, the boiling points, are so different because of the difference in intermolecular interactions, intermolecular attractions. So there's no dipole-dipole interaction. We have lower boiling point, lower melting point, and it would affect other properties as well. So hydrogen bonding, we should have heard about this with our intermolecular forces. This is only possible when we have a hydrogen that's right next to a really electronegative atom, such as oxygen. So we see with water down here, this OH bond can hydrogen bond. This positive portion of the hydrogen bonds with the negative portion of another water molecule over here. We can also have hydrogen bonding between NH. Right, so we have our positive portion, our negative portion of an ammonia molecule, and the interaction that results. So these hydrogen bonding attractive forces, these are a slightly stronger dipole-dipole attraction. So we can see that it doesn't only have to be OH and OH, but we can also have OH and NH if we have mixed compounds. But here we have, again, just an OH-OH interaction that results with this molecule. And note that these hydrogen bonds are still about 20 times weaker than covalent bonds. So we're talking about intermolecular interactions here, not the covalent bond itself. So that's an intramolecular interaction. So these are between molecules. We see hydrogen bonding. Then we can talk about, this is something that you probably haven't seen before, but we're going to define some solvents, whether or not they have hydrogen bonding possible as either protic or aprotic. So solvents, right, that we're talking about again. that can H bond are protic, right? They have this proton bonding, right? H bonding. And then solvents that do not H bond, so no H bonding, are A, which is the prefix used to say no hydrogen bonding, so an aprotic solvent. So we have acetic acid, protic, can hydrogen bond, diethyl ether, aprotic, no H bonding, right? And then we have some more down here, DMSO, dimethyl sulfoxide, another aprotic solvent that's commonly used. So again, H bonding, depending on what isomer you're talking about, these are three different molecules down here with different arrangements. And depending on how many sites of hydrogen bonding are possible, so we have 0, 1 hydrogen bond that can form, or 2, we see this trend of increasing boiling point. So the propylamine, the one that can do the most hydrogen bonding, has the highest boiling point. So you should know how that intermolecular force, specifically hydrogen bonding, affects boiling point. We'll just quickly look at this. H bonding is definitely one of the contributing forces within your DNA. So that's important, in addition to this alpha helix protein folding that can occur with hydrogen bonding. There's sulfide bonds in there as well, different proteins. And then we also have, of course, the weakest force, these London dispersion forces. So that brings us to cases where we have no dipole. Note it in our bonds, molecules are nonpolar. They still have these attractive forces between them. And again, these London dispersion forces are the name given. They can have electrons spread out evenly, which causes this balance of charge, right? Usually, completely nonpolar molecules will behave like this. But we note, if we talk about molecular orbital theory, the electrons are in constant random motion, so we can have a distortion or an induction of charge, an imbalance of charge that creates this interaction. So these are two of the same molecules here. Notice that some of the electrons have shifted towards this side, which creates this temporary dipole, this uneven distribution due to induction, right? And then we have this side of the molecule, the electrons have shifted from, right? So the electrons are going here, the electrons are going here. And we can see that this temporary dipole results, and then these London dispersion forces exist, and we have interaction between two molecules, but they're fleeting, so they come and go, and they're generally the weakest of the forces that we discussed. But if you have a large enough molecule, these can add up and become pretty significant when you're comparing size of a molecule. For example, the more carbons you have in a hydrocarbon chain, the higher the boiling point because of these London dispersions. And we'll look at one other effect of the greater the surface area of a molecule, right? So I was mentioning the larger hydrocarbons, the more of this London dispersion, this temporary dipoles that are possible. And there's a whole discussion in your textbook about gecko feet, if you want to check that out. And then this here shows us that correlation that I was referring to. So we have a 4-carbon chain. Butane boils at 0 Celsius, pentane, more London dispersion, drastically higher, boiling point 36 degrees higher. And then we have our hexane, so now we have added 1 more carbon versus the 5 here, and we've increased our boiling point that much more. So there's one last topic that we'll discuss on boiling point specifically. We'll compare and the structure of our molecule and the resultant London dispersion forces or London interactions or attractions between molecules. So pentane is linear. This has a pretty high surface area, right, where these interactions could occur between other pentane molecules. Now we have methylbutane, which is branched. So that's the effect of branching that we'll talk about. This one is, half of it is branched and the other half is linear. So we have less intermolecular interactions, less London dispersion forces. So we have a lower boiling point. And then if we kind of look at this molecule here, we can see that it's completely branching, right, from that central carbon atom. We have 4 branches coming out, and therefore the lowest boiling point due to the lowest London dispersion forces being present. So you should note all of the properties that are affected based on these intermolecular interactions, and we will continue with another property, specifically solubility, in the next section 1.14.